Okay, so this is being recorded. We are starting now our 10th synchronous lecture. So this is penultimate one from this term. And what we're going to talk about is once more open quantum systems, which is the last topic that is being covered in the syllabus. So let me make a share. Okay, here we are. And to start with, so let's, some people are still coming. So let's start our presentation. Okay, so this is our 10th synchronous lecture. If you want to relate with the online videos and the asynchronous lectures, you will find that we'll cover today Markovian evolution and the Lindblad form of the master equation. These are things that are quite useful. For the asynchronous lectures, either use this hashtag, or if you're intercollegiate and cannot look at MS streams, go to YouTube, you'll find all of them, and some of the synchronous lectures too. And just that we see, we have covered all of this, which is a lot. So we're going well. And today we intend to talk about specifically Markov approximation and the Lindblad form. And just to recap, last time after we have discussed the exercise sheets, we talked also about superoperators. And we were concerned about the superoperators because we wanted to write these superoperators in the Krauss operator sum representation, because we want to describe the evolution of open quantum systems in a way that is not that unitary time evolution operator that we have studied, because we know that it's very good to describe a closed quantum system, but we know if a closed quantum system is pure and you use unitary operators to describe this evolution, it will remain pure. If it's mixed, it will remain mixed, but nature is quite different, and you can have entanglement with the environment. You need to determine what the environment is, etc., etc. So because of that, we would like to write an evolutional equation for this type of system, and starting from the density matrix formalism. So that's why in the last lecture, we briefly recapped what you would have in terms of density operator, how we write the time-dependent Schrödinger equation. So we got to the von Neumann equation, which is a way of describing this unitary temporal evolution. But what if we open now the system? And I'm going to make it clear what I mean by opening the system. So we had a few exercises also that you could try at home. So pretty much, if you have a superoperator that is Hermitian, trace preserving, and completely positive, then this superoperator can be written in the Krauss operator sum representation form. By completely positive, we mean that the eigenvalues remain positive even if you transform. If you have Rho and you apply the superoperator in Rho and you go to Rho dash. This is not trivial because sometimes you have an operator which has positive eigenvalues, you apply a transformation, and this changes. For instance, if you have sometimes compound systems. And if this happens, then you can write in this Krauss operator sum representation, which we are going to use to derive the Lindblad equation. Just to remind you, a superoperator is a mathematical object which transforms one operator to another according to this. So you have Rho dash, which is S applied to Rho. And the Krauss representation is if you can write this superoperator written like this. So you can see you have a sum of linear operators Kj. Each of these are performing a transformation in Rho. But because you have the sum, you situation that you are generalizing what we have before. So Kj are linear operators and they satisfy this. Kj dagger Kj equal to the identity operator if you take the sum. And we need to here talk about complete positivity, that positivity, because we said, okay, Ho has to have real eigenvalues, so this is what we call positivity, but this must be strengthened into complete positivity, and I'm going to explain what this is. And what we really want to avoid, and we have seen here in this course a lot about compound systems, is that sometimes you have an operator or a superoperator, and if you apply it to a reduced state, it never has a negative eigenvalue, but if you act on the full state, it may have negative eigenvalues. And in fact, this is something that people use, as we're going to see very quickly, to characterize entanglements. So this is important if you are a person working or intending to work on quantum information and related topics. And for instance, consider a positive but not completely positive map. So given a real basis I in a Hilbert space HS, the action of the transpose on the basis elements Ij is to swap. So if you have here this operator where you have cat I and bri j, you pretty much swap it. And you can see this very easily in a 2 times 2 matrix. Let's say you have this matrix X, A, B, C, D. This is A, 0, 0. So it puts it in this place. B, 0, 1. So it puts it here. C, 1, 0, and G, 1, 1. So you can see these different ways of representing this operator. And if you transpose, you swap. So in fact, you can see that diagonal terms, they remain the same, because if you swap, it doesn't really matter, the indices are the same, but here the anti-diagonals, they get swapped. So I'm telling you that this is positive, that this transformation and this mapping that we are doing by doing this transposition is positive. How can you verify this? Well, you can show that if the eigenvalues of X are non-negative, then those of Tx, where Tx indicates the transpose of X, are non-negative too. Now, a way to prove this is to look at the roots of the characteristic polynomial, which you can obtain from X, and this is what we call here Px, because if you take this determinant of this characteristic polynomial, a determinant is invariant under elementary column and row operators. So we know that it's not going to change if you do a transposition. So if you calculate that X minus lambda I, this is going to be equal to that of the transpose. Here we have applied linearity of these matrices and of this transposition property, actually, because transposition is linear. And here we consider that the transpose of the identity matrix is itself, so that we can actually see that we have obtained a characteristic equation for the transpose, which is equal to this one. So we can say that the eigenvalues, they remain the same. And if the eigenvalues of X are real, this means that the eigenvalues of Tx are real. Real as well, but I wanted to go for positive. Yeah, it's true for real, but I wanted to go for positive. If the eigenvalues of X are positive, then those of Tx are also positive. So we know this is a positive map. Can we say it's a completely positive map? So for T to be completely positive, we need to check that any extension of T to a compound state space is going to remain positive, okay? So this is another issue, because here we have proven this for a very simple system, 2 by 2 matrix. But what happens if we start to go to bigger systems, which is something that we actually aim to do if we're talking about cross operators and constructing Lindblad equation, etc., etc. Okay, so for instance, this is one example. You take a partial transpose. So now we're going to a compound system. We know how they operate in the subspace HS. So we consider we have this TP, whereby T is going to transpose our system, but we have the tensor product with this other operator, which is just the identity operator. So if you have a compound state space HS tensor product HR, so these two are the subspaces of this compound Hilbert space. And if you want to see how this acts on a basis element, an arbitrary one from this compound state, you're going to see that it is only going to swap the indices of this first guy, right? So the Bryan cat only gets swapped here because here is the transpose which acts upon the subspace HS. The other one is going to remain the same. Now, we could do a very abstract proof, but I'm going to just do something intuitive so that you can see how this works. Because we would like to prove that TP, as defined here, which is the partial transpose, is not a completely positive map. So we're going to consider an example when we have talked a lot about simple spin systems here. So this is actually an entangled state composed of two spins, two down and two up if you want. And we consider then ρ, which is a density operator constructed using this psi. And we will apply then TP, and we're going to show that the eigenvalues of this guy may be negative. Note, you just transpose partially. Okay. So if you apply, you know what you're going to swap. You know you're going to swap here, you have S and R. You are going to swap only here in this case, subspace S. So you're going to swap these first indices here. And that's what you see here. To compute the eigenvalues of this matrix, note that now we have a 4 by 4 matrix because we had two 2 by 2 matrices and we performed the tensor product. Do have a look then. Write it, it's convenient to write it in the matrix form because you can use this and you can calculate the eigenvalues, just compute the eigenvalue equation. And you find 3 positives and 1 negative, so not all of them are positive. So what you see is because you had a partial transposition and you went to a system, that these then became this has changed something that was positive, had always positive eigenvalues, to something that is not positive. Not all of them, at least. You have this guy. So you know that this is a positive mapping, but not a completely positive. And as a consequence, I can say that this transposition does not have a cross OSR, which is operator representation. So it's not a quantum map that we're going to be used here. And this is interesting because if you have a maximally entangled 2-qubit quantum state, which is what I had when I started, let's get a simple example and then let's have a look. And you get a partial transpose and you see you have a negative partial transpose, then you can use this to check whether your system is entangled. Because if you look at a separable state, the separable states are going to have positive partial transpose because it's like one state is not talking to the other. So it doesn't matter what you do with a subsystem. Conversely, a negative partial transpose is going to imply entanglement. So this is a necessary condition. This positive partial transpose is a necessary condition for separability. And it's also sufficient if you're dealing with 2 times 2 and 2 times 3 matrices. It changes if you go to bigger dimensions. This is an issue that we're not going to discuss here, but my point is that this mapping, which seemed quite abstract, and for those who have looked at the asynchronous lecture and the lecture last week were here, You could see that this seems quite abstract, but this has an immediate application for those who are looking for entanglement, which you can use this mapping also first to establish whether you can write your superoperator in the cross representation, and second to establish whether your system has entanglement. So for instance, this specific example, which was this partial transpose, you can see that it can detect entanglement. And if you want to know more, this is a really nice material, which is only on open quantum systems. This is a set of lecture notes for a whole semester. So you see, I mean, we're seeing these in 2-3 lectures. You cannot see these in that much detail, but I'm putting this reference here because I understand that many of you are going to need this in your work. Okay. And any questions? You're quiet today. If you have questions, do put them in the chat or raise your hands. What we are going to go through now is the description of the interaction system plus environment. And this is something is very important if you're looking at big systems with many degrees of freedom. If you don't know also how to describe the full dynamics of the system, because I mean, naively speaking, one thing that you would think about would be just look, what is environment? Why can you close the system? Why can you not say that your system and the environment are a closed system? Make a bigger system. And you know that if you have a closed quantum system, this is going to evolve unitarily under the time-dependent Schrödinger equation. Yes, but do you know what to include? If you have a huge molecule with, I don't know, hundreds of degrees of freedom, if you have a nanostructure that you need to treat, if your environment is the universe, how do you deal with this? I mean, because your environment is everything that is not playing a huge role, but is playing a role and is influencing your system or the system of interest. So you may end up with something that looks rigorous, but whose evolution you may not treat and you may not compute. Then you look and you think, what do I do with that? So this is really something to think about, and is something that could be of concern. So what you could try to do, we have actually seen how to deal with density operators, and we have actually seen that in many cases, we can trace out parts of the dynamics if you have two subsystems that are coupled to each other, right? So why not use this principle to derive an evolution equation for just the reduced state of the system alone? But then you need to know how you're going to treat this environment and what you're going to do. So let's look at the time-dependent Schrödinger equation. What do we have? Here we have a time derivative, right, of your cat. And we have an operator O, if you look, which is minus I, the Hamiltonian divided by H bar. But we could look at this form and we could say, okay, so we could try to write something for the density operator to describe its time evolution, which looks like that, which has on the left-hand side a temporal derivative, and on the right-hand side has a super operator, which is an operator of an operator. So this is a mathematical entity that is changing that operator. And that's what we are aiming at today. So last lecture talk about von Neumann equation, which is another way of writing the Schrödinger equation, but in terms of whole. And today we're going to look at this definition of derivatives, and we're going to play around with this concept so that we are going to write an equation for this super operator. So let's, for this evolution of O. So it's a first order differential equation. On the right-hand side has a super operator, which we don't know yet. We're going to try to come up with something. Actually, some people have tried before us, but we're going to try this here in this lecture. And we would like then to use, we're going to start from the definition of derivative. So we're going to write then this definition, which we know that rho dot t is the limit of delta t going to 0 of rho t plus delta t minus rho t divided by delta t, where this delta t is like really, really, really small, infinitesimal. And we know that if you take that to 0, that delta t, the derivative is in fact a limit, is the limit of this expression of, we can say that rho t plus delta t is rho t plus the derivative of t multiplied by delta t. And what is the consequence of this? If we look at this expression, there are a few things that we can see from the maths. In fact, we can see that rho t plus delta t is going to depend on the density operator at a time immediately before. So rho t plus delta t is going to depend on rho t. This is one thing that we can see, right? This expression is connecting both. We can also see that the system evolution cannot depend on the state of the environment, because we're just writing something here in terms of rho t and rho t plus delta t, right? And also, if you have a state of the system for an earlier time, before those that we are connecting, because we're talking here about t and t plus delta t, but how about t minus delta t? How about some earlier time, some previous history? I mean, this equation is telling you that we're trying to describe this evolution just looking at t and t plus delta t. So if you want to establish a history for the system and say that that history is influencing time evolution, this is not embedded in this equation. So this is what we are going to call Markovian evolution. And the way a system is going to change will depend only on its state now. And we are going then to go for it, and we're going to try to establish an expression to describe this evolution. So it's not, the system now is not being influenced by the change that happened like ages ago, but only what previously happened just right now. So what happens in the future is influenced by what is happening around now. So you're going to reset the whole thing. And note also that this evolution is depending only on the reduced state. Here, this whole is reduced state. So the environment is not influencing it. So that's not, what I mean is that the information here is only flowing. I mean, it's an open system. We're assuming the system is open. We don't yet have the expression. We're just looking at how the density operator would evolve. So we are assuming then that the information is going to flow only in one direction, which is system to the environment, that the environment is not influencing the system back. Okay, if you drop this assumption, then you're going to go to no Markovian evolution. And most actually quantum systems that are interacting are no Markovian, the evolution, because you have this influence, you have this influence of the system, of the environment back into the system. You have some kind of history. Actually, there are whole fields of research on non-Markovian evolution. So, but we can treat quite a lot. And if time permits, next week we're going to see an example. So one example of Markovian evolution is spontaneous emission. We can have some types of random walk as well, DNA models, problems in statistical mechanics and thermodynamics, and this board game of snakes and ladders. I don't know if you have the opportunity to see the asynchronous lecture. Gonna see even, I put even a real snake there, but okay, there was a joke. It's just because in the snakes and ladders, what you do is you progress and then the game is somehow reset. And this is a bit the idea, that we just consider what happened immediately before, and we don't go further down temporal line. So, okay, I've been talking a lot about Markovian evolution, but how would you describe this evolution then? Let's check. Okay, one can do the following. We could write a Hamiltonian for the full system and environment. You can do that, right, in principle, and then you could trace this out. So you could perform a partial trace over the environment, and you would then manipulate this expression. I mean, the advantage is that would be really rigorous if you did that, but you never know how the derivations are going to be, depending on the system they have. This could end up being horrific. And they are also quite Hamiltonian specific. So there are drawbacks, there are advantages. I mean, I'm not saying don't do this, because you need to weigh, say, if you're dealing with a real life situation, you need to weigh the problem that you're trying to solve. Okay. And you can then manipulate the expression. Fine, if you get something is rigorous and it's nice, but it's going to be Hamiltonian specific. And another possibility is to try to do something that is a bit heuristic. So you can do something that is general, and you can come up with a general form in which all the Markovian master equations can be expressed. And you can try to understand this equation phenomenologically by putting things which you realize, observe in the system that you're trying to study. After all, you're trying to model a physical system. Ideally, if you're doing research, you should try to do both, because you need to have some checks, okay? But again, you need to weight the situation. So what do I mean by phenomenological? Mean that we are going to associate operators in the master equation to observed events. We're going to make educated guesses. And this is going to be based on the phenomena that we're trying to look at. So the lecture 9, part 2, Markovian master equation, actually deals with that. And there is a derivation which is really detailed on iPad. So what I'm going to do now is I'm going to go through the main points, like greatest hits, if you wish, of the derivation. So what we are aiming at is we would like to derive an equation which is of this form. So on the left-hand side, we have the temporal evolution. And on the right-hand side, we have a superoperator applied to whole. And we're going to start from this expression. So it's pretty much using the fact that the derivative is a limit and is given by that, whereby we're connecting then whole t and whole t plus delta t. And what we really don't know is whole dot t. We don't know this derivative. And what we would like to do then, because if we do that, we are fine, right? Is to derive an approximation for whole dot t, which is accurate to first order in delta t, whereby this delta t is super, super, super small. Okay? Assumptions, the evolution is Markovian. There is a superoperator transforming whole t to whole t plus delta t. And the superoperator can be written in the cross operator sum representation form. And that's why we were insisting, and even there was this example, okay, you have this operator and it cannot be written like that because one condition was missing. Because if you actually need this to be able to derive the Lindblad equation, which is what we're going to see, or the Lindblad form of the master equation. So if you are trying to do some research and you want to cook up an operator which cannot be written in this form, then you better look for something else. Or you know that this equation is not going to be applicable. So this is, it needs, can be written. This is really, really, really important. And we have seen that there are a series of prerequisites which tells you that this is the case. So if you want to look at the Lindblad form of the master equation, we need then to set t equals 0. So that we don't need to, but makes your life easy. And if you assume that the time evolution is not changing, depending on where you start from, which is a reasonable assumption, why should it? Then we set t equals 0. So that whole delta t is equal to whole 0 and delta t whole dot 0. And from this assumption, where we said, okay, we have this super operator of whole 0, which is actually describing my time evolution, then we can write that also the super operator can be written in the cross operator sum representation form, where kj and kj dagger are linear operators, and you have a sum, and you have a sum of linear operators, and you're applying this upon whole naught to make the system evolve. Is legitimate. So we have only made legitimate assumptions. Okay, these are assumptions, but we are pretty much confident because we are paying attention to trying to make this consistent the whole time. So if we compare both equations, we see, like, if you look at the expression that you have here, and if you look at the expression that you have here, they have to be equal, right? So we can say then that K naught has to be of this form, because you have here whole naught, and then you have here this delta t, and then you apply to whole naught. So it needs to be of this form, and there may be kj where you have square root of delta c lj, and these are both a and lj are linear operators. So if we insert this into whole, then we have this expression, and we're considering the whole sum, right? So it was from 0 to infinity, so this is what it should be for k0, which we found by inspection. Then you go from j equal 1 to infinity, and you then have to do all these computations. So you need to compute this term in which you're transforming, but with k0, you have the explicit expression, which is given here. And you have also this guy, which you got by making kj square root of delta c lj. So our aim here is to get an expression that is linear with regard to delta t. So once you do these multiplications and these operations, you find you have whole 0 delta t a whole 0 plus delta t whole 0 a dagger. So it seems we're getting things here that are interesting, and something that is of the order of delta t square, which we're going to neglect, plus delta t, and then you have this whole thing here from j equal to 1 to infinity. Okay, so we are making some assumptions, and we can, from the form of the time evolution of whole that we have realized exists, and we end up then with this expression. And if the evolution is the same for all times, which was the assumption we have made not to carry t around anyway, because we wanted to avoid certain expansions, and is a legitimate assumption, then you can say that whole dot t is a whole t plus whole t a dagger plus this j going from 1 to infinity lj whole t lj dagger. And next, what we're going to write is this is, we're going to write A as a linear combination of two Hermitian Hamiltonians. And you can do that. A, you have no guarantees, so it's non-Hermitian principle. But we can write, we don't know what M is, we know what H is, and we write K naught as like this. We use also the fact that if we have these Krauss operators, where is it? Yeah. If we have these Krauss operators, that their sum of Kj dagger Kj has to be equal to the identity operator. And what basically we do is we use this expression for K naught, we retain terms up to the first order in delta T, and then we find M, because remember, we didn't know M, we're just postulating. Okay, we don't know what this operator is, then it's possibly non-Hermitian, but we can write as a combination of two Hermitian operators because they have some nice properties that we can use. And we know what H is, we're assuming it's the Hamiltonian. We want something similar to the time-dependent Schrodinger equation, right? And we put some M here, which we don't know, but we can calculate. So that's what we have done then here. And this is going to give you this type of expression plus the rest of the sum. And if you look, you see that this is like an effective Hamiltonian, which you can define apart from these factors here. So you can say this is H effective, where this is H minus I, H bar divided by 2, sum from J1 to infinity to Lj dagger Lj, so that your equation then becomes this. So what you have is, you have then what we call the Lindblad form of the master equation, where you have whole dot T is given by this, whereby this is H effective. So it's like a commutator, can you see? And maybe you remember the von Neumann equation, where you had this, but in terms of just the Hamiltonian, and you didn't have this other term, right? But now we have, instead of H effective, we have this commutator with regard to commutator, more or less, because this is non-Hermitian and it is more general. It would be a commutator for H, okay? But you have anyway this difference, and you have this extra term here. So one thing is HF is non-Hermitian and has complex eigenvalues as well. At the very beginning of our lectures, I said as an example, okay, you can have situations in which your Hamiltonian is non-Hermitian, it is going to describe decay, coupling with the environment, for instance, or you can have a situation in which it's non-Hermitian but has real eigenvalues, which is totally different from here, okay? So now you see that you have this expression and you have this guy, which is your effective Hamiltonian. And this is signaling the coupling of the environment. So if this didn't exist, you wouldn't be coupled to the environment, you'll have something Hermitian. So because you couple with the environment, you are going to allow for complex eigenvalues, and you are going to have something irreversible, which makes sense. Remember that we made that assumption that is going only in one way, it's not coming back. This Lj here, which you see here, and you see here as well, they are known as the jump operators. And what happens is that they represent the irreversible processes associated with the interaction with the environment. For instance, if you have an environment making something go from the excited state to the ground state, or if you have some degree of freedom that you want to include, I mean, you have to be careful how you define these operators, but you can have a lot of freedom in that. because you can use this then to represent this interaction, and you can do this phenomenological by observing how your environment behaves. And also that the assumptions that we have used here, and which you can see in more detail in the synchronous lecture, they were quite general. And what this means is that the evolution equations of open quantum systems undergoing Markovian evolution will be of the Lindblad form. So this is covering like a huge class of systems. Remember, we said at the beginning, you may have something that is system specific and is rigorous, or you can have something that is more phenomenological, but is more general. So that is pretty much what we have achieved here by making this derivation and making these assumptions, which are implying that you have Markovian evolution. So particular case, if the jump operators, which are those describing this connection with the environment, is equal to 0, we then have that H effective is equal to H. So then we are going to recover the von Neumann equation, which is given by this expression, which is a way of writing the unitary evolution of the system in terms of the density operator. And there's some nice application which we're going to see either next week or in the practical. I'm still deciding where I'm going to put this, but it is related with a sync. Do try at home in any case. I know a lot of you are still finishing your exercise sheet, but to give it a try, a single spin half particle is prepared in this state spin up, and it undergoes evolution via one of the following superoperators. So we're given some superoperators, and for each of them, specified in terms of the Krauss operators, compute what is, if you apply the superoperator to this state, to this projector associated with a single spin half particle prepared with spin up. And then you have these Krauss operators given here, S1, and then you have S2. So you define two superoperators. This is really just to get you going, and that you get familiar with the notation, and then you play a bit around. And you can also use Pauli matrices with regard to spin, and do have a look at also, there are some examples of spin decomposition that we have covered already and they are in lecture notes. And you need then to write this in the Krauss representation. So you end up with these kinds of expressions. So if you apply the superoperator, then you get both up or both, you get two projectors, one with both spin up and the other with spin down. And also have a look at if you can get this expression. And it may be useful also to check these. Do give it a try. We're going to see it in more detail on Monday and Wednesday, but it's always good to give it a try. I'm putting also other stuff there on top of this. And thank you for your attention. You've been quiet today. Do ask questions. I don't know if it's because people were concerned about the exercise sheet, but it is an important time to ask questions also. We all have questions and comments, and it's really good to learn. You shouldn't be embarrassed or anything, okay? So take good care of yourselves. Last week is going to be the last lecture. I think we will. Yes, there's no strike, and I think it's the last week. So we are having every second week, so we'll have practicals. But I'm going to check again, okay? This week, it was like, last week it was, okay, you have strike. I didn't know if Robert was striking and what the situation was. So I wasn't really sure. And we are not, if someone is striking, we shouldn't tell you before that we're going to strike. People can if they're nice, but I'm not going to go to my colleague and ask, are you striking? So it's a tricky situation, if you know what I mean. But there should be. on Monday and Wednesday. And we're going to have this last part, just that you give it a bit of a try and get used to this notation. And also something with axioms, because I think we need to get a bit used to that as well. Okay, so take good care of yourselves. Have a nice week, and see you next week in one way or another. Take care. All the best, and stopping the recording.